Take Talk Tuesday. Come on in, my friends. Hey, Chuck, number one in Georgia. 6 o'clock, Georgia, Eastern. It's 5 o'clock in Tennessee time. Hey, Brad. Interesting stories to tell you today. Talk about some port shapes and sizes. Talk about some things that I've learned and think I learned. Hey, Joe. Thank you all for signing up. We'll get in here in a minute. I'll get a few folks signed up on here, and then we'll go in there. Hey, Ed. How's it going, man? Hope y'all are doing well. Hey, Joe. Thank y'all. Hey, Ron. Charlie. Good to see you, Charlie. Back in Georgia, I hope. Hey, Sean. Thank y'all for tuning in. In the background, you can see Blue 50. That's one thing we're going to talk about today, but I wanted to share with you that this episode today is going to be about port sizes. It's going to be about cross-sectional area. It's going to be about how important that is to us and what I think I've learned over years. There's some, I'm a big port guy. I'm going to show you some today. I got some stuff to help you understand a little bit more of my viewpoint maybe. This valve right here that's in the NHRA Pro Stock motorcycle, this is a 2.8 intake valve. It's really big. The 311 stem. It's very lightweight, but it's really big. But that's what we have been running at the NHRA. Like Matt Smith has in his Buell, and some of the other guys that are running the 2 cylinders. The Suzukis have 2 intake valves like a Milwaukee 8. But hey, Jim Bob, I want to tell you a little bit about it. And there's some guys on here that are great friends of mine, and I love y'all, and we don't always agree on stuff. But hey, man, I don't have a problem with you not agreeing with me, and I hope you don't have a problem with you not agreeing with me not agreeing with you. Right? We can agree to disagree because we all know what we think we know based on what we have done and what we have learned. And I am always interested. And when I say something on these stories and these shows on Tech Talk Tuesday, when I'm wrong or somebody points out a good reason, of why I may be wrong. A couple things today I saw where I messed up on my math, but I am thankful for the folks that are on here that look out for me. They're not like trying to throw me under the bus. They're not trying to say George is wrong. George said this wrong. George did this. No. Hey, Tom, Barry, we are sharing information. It just so happens the good Lord blessed me with the opportunity to be able to come up on here and talk and share some ideas. And I've been very fortunate to have spent all of my 70s, all my 80s, my 90s, my 2000s, my 2000 teens, and over 2020 learning about engines and getting to share it with you guys. So this story is going to be about big engines, big ports, little engines, little ports, but it's going to be how we can use some of this information to our best advantage. I'm going to turn over now. Well, first thing, just for a little fun, I think it would be great to show y'all the big engine on Blue 50. I did get the cylinders on it. And I was in the process of finalizing my deck height. You can see that pistons look really nice coming to the top. And it's confusing to folks because in reality, this rear cylinder is like a single cylinder engine all by itself that's dead nuts, straight and true. When it's at TDC, let me turn it all the way up. When it's at TDC like this right here, that means that the wrist pin, the rod pin, and the main are all lined up perfectly. And when you move over to the front and you bring it to the top, this is also a complete single cylinder engine by itself. It's just one of them is leaning forward 22.5 degrees off center. This whole engine, this front engine, is leaned over. So if I was to tip this engine up in the bike, tip the engine back 22 degrees. This one would be straight up and down with the crank straight under it. And this one would be 45 degrees behind it, straight up and down. And when, just like a radial engine in an old airplane, they don't know which one's straight up. They don't know that one's on the bottom and one's on the top. This engine thinks both of the cylinders here are the most important. So I'm going to tip this way so you can see this is like a single cylinder engine with the piston coming to the top. And then the rear is like a single cylinder engine with the piston coming to the top. So it really goofs up the fact that both of these are on the same rod, on the same pin on the crank. So that makes them come to the top at 2 different times. Try and drop back so you can see. And you see how they're taking turns at the top? I just thought I'd share that with you. Now, you can see that what I'm doing here is I'm going to learn about exactly how much I got to cut off of the cylinders, how much we have to cut the deck. And when we do, then that will help us decide what base gasket thickness we're going to run and what kind of piston to head. And I'll talk about that a little bit also. All right, changing over to the board now. This is the real deal right here, y'all. Tech Talk Tuesday, number 167 today. 167. Telling me to rotate my phone. Okay. And I got a little dilly here that some of you have heard of. And if you've heard of it, that's cool. But there's no contest here. Brad, you'll appreciate this. Harvey, Lloyd, check out these deals here. This little thing here. This is a compensating planometer. You may have heard of one. Hey, Paul. Hey, Scott. If you haven't heard of one, we're going to learn about it today. And I'm going to tell you something that I have learned about it, and I hope that this video will let me show what it does. But I just freehand sketched 2 shapes. One here is kind of a rectangle, like a rectangle small block Chevy or big block Chevy, but it's 1.5 inches wide and it's 2.3 inches tall. And what I did was I used my vernier caliper and I went in here and I measured the width and I wrote it down here, and then I measured the height and I wrote it down here, and then I used my little baby calculator. It's not my ARRP calculator, but I used my baby calculator, and I said, if this is 1.56 inches times 2.35 inches, this should give me a square inches of 3.66. All right, I'm gonna do it again since I got a different number. 1.56, we got that, everybody, right? Times 2.35 equals 3.66. So I'm gonna write that down right here. That gives us 3.66 square inches within 1/10 in here. All right, now I'm gonna show you this cool little tool. Let me put a little equator here. Can y'all see me okay? All right, here's the little equator. That's gonna be my start and stopping point. I'm gonna set this little gizmo up on here, which is just this. It's really weird. It's just this little arm that pivots in here. And if you've seen one of these before, you're the coolest kid watching today. But this, back before we had 3D programs and all the design programs, this is how we figured area of a port or a shape. One I did is I put this at 90 degrees. I zero this little gauge. This is a little cheesy little deal. I zeroed it right there. And it's got crosshairs like a gun right here. And my hands are shaking a little bit because adrenaline's kicking here. But I've got this on 0, I got this on 0, and I got this crosshairs on it. So I'm just going to sit here and I'm just going to trace this line just kind of inside or just on top of the little purple mark. I'm going to try and make it as smooth as I can. I'm not doing it perfect because this doesn't matter. It's not science. And then I'm going to stop at the equator. Then I'm going to go over here and look at what this says. It says 3.6 inches right here. Isn't that bizarre, y'all? Look at this one. This is a nice oval port. It's 2.6 tall, 2.1 wide, 2.6 tall, 2.6 tall, and 2.1 wide. That came up, the math gave me 5.5 inches, but we know that can't be right, y'all, because look, this area is missing. This area and this area. So we know it's not going to be 5.5 inches because all of this is filled in. All right, let's try and measure it. I'll set it on this little equator, and I'll set this to 0. I hope y'all can see this little tool. Oh yeah, maybe you can see this one now. I'm gonna set this on 0. Look at my hand shake, y'all. I hope one day you get to be this old and enjoy doing this stuff. All right, I got this on 0, and I got this crosshairs on the equator, and I know you can't see both, but I'm gonna trace this shape out, and you'll see me come by in the corner of the picture. I'm gonna trace this out, trace it out, trace it out, and trace it out. And I'm gonna come over here to the little equator and stop. And right here it says 4.85 inches. This is what the oval shape would be here. Even though if it was rectangle, it would be 5.5. It is really 4.85 in reality. Let's do something really crazy. This is something that's pretty easy. Somebody that's good with math, is we can take this valve and we can figure the area of this valve. And figure out how to do it. I'm so excited. When I was moving here to Tennessee, I found this thing in my desk drawer, and I just hadn't been in my desk for so long. But this is 20, 30 years ago, back when we were winning a bunch of races. We had a leg up on everybody because we could find out what our cross-sectional area was before there were programs. And I'll tell you, there's other ways we did it to learn. But I'm going to move this over again. Please bear with me on how much I'm shaking this. This was just fun to share. All right, I'm putting this gauge on 0. I got my crosshairs inside this valve, and I'm going to measure the cross-sectional area of this valve by tracing inside this purple line. Without being really careful, I'm just going to get approximate. And it says that this valve is 5.75 inches in area. So if somebody has some handy dandy math, they can check that for me and see right there what that says. Isn't that funny? So we don't need this kind of stuff anymore because we have all these cool programs. Well, let me tell you how I used it to win races and to set records. So we had these really fast engines, and we started like this one right here. This is a Chrysler Hemi. This is a regular 426 Hemi, iron head cast. We took this rubber molding compound that we used to do all these ports. Like here's the Buell, S&S Buell Pro Stock intake port. Like this isn't like the one Matt Smith's running, but this is the style port that goes with this valve. You can see how this port goes with this valve. So we put this 2-part compound down in the port. You pour it in there and you let it set overnight, and then you can take a screwdriver and stick between the port and this stuff and shoot a little WD-40 in there, and you can worm this baby right out of there because it's rubber. And you can use this to measure stuff like same as you can the ID of the port. You know, you can go in here and say, oh yeah, this port is, what does this say? This is 2.7 inches wide, and right here it's 2.325 tall, You see what I'm saying? You can do it like this and just get some roundabout numbers like we did over here, where you could get 5.5 inches here. In reality, we were running 4.85 as far as what the air was having to get through. So what did we do? Well, we wanted to know where the choke was, or the minimum cross-section in the Hemi was, is we cut the intake off and we sliced it up in lots of pieces, and then we measured the cross-sectional area. And I'm going to show you an example of this amazing process. And you please understand now, I know this is old and historic, but I've been wanting to share it with you. So here's one that went really fast and we won races with. This is one of those intake ports that we did the molding compound on. And when you take this and line it all up, this is a perfect port of a really, really this is a model of a perfect port. I don't have to have a CNC machine. I don't have to have CAD to do this. I just drew a center line down the middle of it, put numbers. I cut it how many inches did I cut this one? I just did approximate because I was trying to find out where my choke was. So I was doing 1-inch sections. So I did 1, 2, 3, 4, 5, 6, 7 sections. This side's where the valve is, where the valve goes in. This side is where the throttle body bolted on, and you can see how big it was. But this is what's really cool. You would imagine that this section would be kind of round, and I took a razor blade and cut it, and you can see it's kind of round. This section starts not being as round, and then this section starts being a really weird shape. And then this section starts being an even crazier shape. And then we start getting back up to the throttle body where we have a round throttle body, and it goes all the way back to round or oval shape over 7 inches. So now we can put this whole thing back together. I'm sorry I'm shaking y'all, but I'm excited about it. I hope you can see this okay. I'm 68 years old now. I'm probably hungry. And when I get hungry, I get a little low on the blood sugar, but I'm in great shape. I'm happy, and I'm healthy enough that I just probably need to eat. But it's time to do Tech Talk Tuesday. All right, there's the big port. How cool is that? All right, everybody watching, everybody load. Okay, let's just go in here and grab this section through the guide. Let's see if I can get a tracer here. I know this ain't popular information, or it's not for everybody. So I'm gonna do the best I can with it. I'm gonna take this shape right here, and I'm gonna trace it. And this is a crappy tool to trace with, but I'm gonna do it for educational purposes. If you're bored, change channels. If you're interested, stay right here because it's coming. Zero the gauge. Golly, next time, y'all, I promise I'll eat first so I don't shake so bad. Set the gauge on 0. And I don't remember any of these numbers, but I do know that once we got all this stuff right, we were hauled the mail. All right, I'm going to check. I'm going to go around here and try and do inside of this line without being too herky-jerky, and I'll get it within 1/10 of an inch. And let me tell you, this is way cheaper than the 3D modeling program that I had to buy to get the 5-axis machine and get it working where we could build our own ports before I retired. All right, that son of a gun came out dead nuts, 5 inches. 5 inches. 5 inches cross-sectional area. What does that tell me? The cool thing is when I put this away, when I finally put this away, I had already bought all the stuff that we needed to scan the ports. I sent models to Exact Metrology up north, had them scan. I sent my cylinder heads and had them scan the heads, scan the chambers, and create surfaces that had cross-sectional areas figured in it. And that saved the day, because at one time there was nobody you could do it. So if you had a team, that was winning professional races, like at the time KB Racing was winning a lot of them, Joe Gibbs and RCR and some of those other teams, and Hendricks, they had hired these guys that had all these programs that were taking this equipment and breaking it down and using it to scan the port, like just scan this, rather than doing a port mold compound, without having to pour the molds in it, then pull it out and cut it. You could scan it, and then you could see that you could actually make a 3D scan on a screen and modify it and change the shape of it to suit what you wanted it to do with it. And it saved us all this trouble. But there was another step before this that I want to share with you guys, and I hope this is not too boring. But Jackie went to the drugstore way back when you would just go to the drugstore to get like school supplies, and they had this green paper, and it was called graph paper. And you could buy it, and let me just show you. This is going to be an exaggerated view, but it had lines like this, and each square was 1 millimeter. And what I would do is I would put my port on that graph, and I would draw it, and I would trace it. This was before I got the planometer. I'd put this on here, and I'd go in here and I'd say full squares, 1, 2, 3, 4, 5, 6, and I would count all the full squares. And then I'd leave these partial ones. Well, that's a pretty good one. And then I would count them, and I would put down how many, 67 full squares. Then I would say this one, and this one, and this one is 1. And then this one, and this one is 1. And I just keep going through here, and it would take 30 minutes to do it, but I could get how many millimeters there were, and then I would figure those millimeters, and then I'd do the math. I would do like 100 millimeters, let's see, what is that, divided by 0.03937 equals 100 squares. 100 squares times 0.3937 equals. That would be 3.93 inches or something like that. But anyway, it was something like that. But that's how I first learned. The next thing I did that was really cool was I got the cylinder head. And I got a welding rod and a piece of aluminum sheet, real thin, like 060 aluminum sheet. And I would weld the welding rod to the deal, and it would be like a little 2-inch disc. And I'd sit it in there, and I'd put it on the belt sander and grind it and grind it and grind it until it would fit in here. And I'd fit it and fit it and fit it until it fit perfect. Then I would put it on the graph paper and trace it out, and then count the squares, and that would tell me my cross section. But that wasn't the important part, because there was so much flow bench data going around. Everything was about the flow bench. You had to have this much flow. You had to have this kind of air speed. So you needed to know the minimum cross section. And back then, all the Ford, Chrysler, Chevrolet guys, they all had push rod pinches. So there'll be like a push rod right here. So they'd have to put a big turn in the port to get around a push rod. And the car guys thought that when they won the race or set the record, that the port had to have a push rod pinch. So they actually called it the push rod pinch. It had a PRP. So when you were talking about porting, you said it would be this kind of area here, and it would be this minimum cross section here, and over the short turn it would be this minimum cross section, and then the PRP, the push rod restriction, it would be another cross section. And when they would finish, it would have a list of them. It has to have this at the manifold, this at the push rod pinch, had to have this over the short turn, and it had to have this at the valve. But that was only what they knew. That was based on data. That was based on real empirical data, where they went to the track, won races, and went back and back traced everything to figure it out. So all through 40 years of trying to document everything we would do, 40 years where we came up with so many ways to measure stuff, And I think it's proper here on Tech Talk Tuesday to share that information that we've learned over time. So, I got distracted for just a second there. Anyway, what it did was we were able to count, make templates, count squares. Then I got, I know what it was. Where I was going next is the graph, the cross-sectional area map. That's the next thing we learned. We did a map. Let me move this up. Man, I don't work good with distractions. I forgot where I was. I'm sorry, y'all. Please forgive me. All right, here's a map. I'm gonna draw what I think it would look like. This is the size of this axis. This is inches, like 4 inches, 3 inches, 2 inches, 1 inch in cross-sectional area. And then this is how long the port was, which I showed you. This one is like 7 inches long. So it would be at 1 inch, 2 inch, 3 inch, 4 inch, 5 inch, 6 inch, and 7 inches. So this would be 1, 2, 3, 4, 5, 6, 7. So what I would do was I would take this and figure the cross-sectional area of number 6, and I put a data point. I'd figure the cross-sectional area of number 7, and I'd put a data point, and then so on and so on. Number 5, and I would figure the cross-sectional area, number 1 and number 2. And what I'd do is I'd end up putting data points, and then I'd connect the dots, and my graph would look like this. This is something that the flow bench didn't show us what we were trying to do, but we would shove a 300 CFM, 400 CFM, 500 CFM, even maybe a 600 CFM port through this. And this right here, this would flow 650, 680 CFM. This valve, 680 CFM through a 28 inch, through this valve with this port shape. But it didn't know what we were asking all of that area to do. And the flow bench was fine with it because it didn't bother making this turn. It didn't mind going from this area to 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 this area. It didn't see it at 28 inches on the flow bench. But in reality, it's going 100, 200 times a second, 200 times or 100 times a second, in and out, in and out, in and out. And we're squeezing it really big, down, really big, down. And at the end of the day, finally in the 3D world, as we ended up with a cross-sectional area that, in my opinion, it looked like this. Every inch needed to be where the minimum cross-section was in the valve job. And it was a certain degree. People say 7 degrees. Some people say percentages. How much smaller it gets per inch. But what I learned in all my years with the flow bench, probably 30, 40 years on the flow bench, that the flow bench wanted it shaped like this. It wanted it to be little here, and it wanted it to be little at the push rod, and then it wanted it to be big over the short turn, and then little at the valve. This ended up being the cross-sectional area shape of a very well-flowed port that didn't make as much power as it should based on its flow. But over years, we came up with all these ideas like if it flows this much, you'll make this much HP per CFM. Okay? Well, which port shape is that? And which cross-sectional area is that? We have to consider all that. But I know I'm running out of time, and I may have lost some of you. But please understand, you guys, this is a result of how this is the tools we used when we were learning how to win and how to keep our edge over the competition. And we were able to win some championships with the late, great John Myers and Angel. And we had, like I said, we were very fortunate to win a bunch of races. I think it was 80-something NHRA national events. But it was, even with the Team Winston days, we had our advantages because it was before CNC stuff, and we were able to go faster and faster and learn from it because we were able to document our changes and learn what things made a difference. So anyway, I know I ran out of time, and I wanted to tell y'all thank y'all for watching. It's been great to see you guys on here. Let me tell you that this is recorded. Jackie's going to put it on our YouTube page. There's 150 Tech Talk Tuesdays on there. This should be Tech Talk number 167. Thank you all for watching. Very thankful, you guys, for tuning in. And may God bless y'all. Look, please look after each other because we're all we got, right? Great night. Thank y'all.